Hello. Today we're going to talk about motion with resistive forces, and specifically resistive forces that are proportional to velocity. For example, if you're driving a car, the faster you go, the more air resistance, the higher the air resistance gets. Same thing if you were to, let's say, drop a ball in some water. As the ball goes faster in the water resistance becomes greater. And there are two different functions, or there are many functions you can have for resistance. The two we're going to talk about today are if air resistance or fluid resistance is proportional to the velocity, and then the next one will be proportional to velocity squared. So case one is proportional to velocity. That's a slightly easier one to math out. Let's say you shove your textbook across a frictionless surface, and the only thing that's going to slow it down is air. And let's pretend that force of resistance is proportional to V. So let's say the book is here, and let's say it's moving to the right. But if I draw an FBD, we've got force of gravity down, we got normal force up, and then we're going to have this resistive force, which is proportional to V, and we write that as kV. It's some constant times the velocity, and it's the opposite direction of the motion. Okay, so we're going to figure out what is the motion of this as a function of time. What's the velocity as a function of time? What's the acceleration as a function of time? Also, we can figure out, if you wanted to, how far it goes as a function of time. Now, at this point, I'm going to tell a story. I like to share the story with all my LT students. If you don't want to hear the story, you can fast forward. I'll write the word end after the story. So when I was at Purdue Engineering, I had a fluid dynamics class, and we learned about these resistive forces. And there's a lot involved with them, like for finding K in that equation up there, there's a lot involved with fluid dynamics to figure out K. That's a lot of what fluid dynamics is. So anyway, we had a problem that was very much like the one I just drew. It was you were throwing a board across flat water, and the water would stop the board, and that force is roughly proportional to V. And you had to spend time figuring out what the constant up there, K, was, and there was some fluid dynamics stuff with that. And so the professor, on a question, now we're talking 200 plus students in his class, it's a second year course. The professor threw a problem like this on the test, and the professor asked questions like find the constant K, what's the resistive force at a certain time or at the beginning. But then he asked us to find velocity as a function of time. Okay, and I was able to figure it out, and I wrote down on the test, no more than 5 students will get this right, which is pretty cocky considering there's a couple hundred mechanical engineering students in this class. Well, sure enough, we get the test back about a week and a half later, and the TA that had graded my test said, "You were right, only 3 of you got this question right." So I'll explain what almost everybody was missing in a second. But this ends my story, okay? So I will make a note. It's the end, so if you want to start listening again, you can. All right, so here's the deal. We're going to start with, in order to figure out velocity as a function of time, we're going to start with Newton's second law. And this is what everybody forgets, is they forget to start off with the basics. And we know Newton's second law is net force equals ma, okay? Now, the only force horizontally acting on the book is kV in its opposite direction of the motion. So we write negative kV equals ma. Now, here's the problem. I want to write V as a function of time. Well, I've got another variable. I've got A. That actually changes with time as well. So we need to write A in terms of V. Well, we should know that A is dV dt. Okay? So if A is dV dt, we'll plug this in. So we got negative kV equals m dV dt. Okay? And we need to separate our variables. We have 2 variables. We have velocity and time. If you do a little math, you would get the following equation. You would get, let's see. we're going to write dv over v on one side, and then on the other, we're going to write negative k over m times dt. And then we're going to integrate both sides. On the left side, our limits, now be careful here, the tendency is to want to put 0 for the first limit. That is not the beginning velocity. When we gave this book a shove and let it go, it had some initial velocity. We'll call that v0, all right? So that's our limit. We start with v0, we go to v at some other point. Time does start at 0, and we go to t, okay? Now, the integral of dv over v is natural log of v evaluated from v0 to v, and this equals negative k over m times t. And technically, it's evaluated from 0 to t, but that's just going to be t. And then if we move this over to here, we get natural log of v over v0 equals negative k over mt. And if you solve for v, you take the exponent of both sides, get rid of the natural log, and then you multiply both sides by v0, and you get the following. V as a function of time equals v0 e to the negative k over mt. So that is your velocity as a function of time. In the process, we can also find the acceleration. Acceleration is the time derivative of this, dv dt, which is, in this case, v0 times negative k over m, and then e to the negative k over mt. Now, you might notice something. You get a negative out of this, and that should make total sense to us because acceleration is negative. The book is slowing down after you let it go, okay? So there you go. You can also graph velocity as a function of time, and you can graph acceleration as a function of time. The velocity starts at v0, and it decays to 0, okay? Oops, and the acceleration would actually be negative, so I should probably start that down here. That value is negative v0 k over m to start with, and that also decays to 0. And basically, when the book stops, it's also not accelerating anymore. So both these graphs do approach 0. Now I'm going to cut this video off here. There is a second example, and then there's a third example. The second example is a little more mathematically complex, but not much. The third example I'll kind of explain. Okay, so look forward to the next video.